Video game graphics have come a long way since the early days of Pong and Space Invaders. Today's games feature photorealistic environments, lifelike characters, and stunning visual effects that rival Hollywood blockbusters. But how exactly do these incredible graphics work? Let's dive deep into the technology that makes modern video game visuals possible. At its core, video game graphics are built on a foundation of mathematics and computer science. Everything you see on screen, from the smallest blade of grass to the most expansive cityscape, is constructed from basic geometric shapes called polygons, primarily triangles. These triangles are defined by vertices, which are points in 3D space with specific coordinates. The process of turning these mathematical constructs into the visuals you see on screen is called the rendering pipeline. This pipeline consists of three main stages: vertex shading, rasterization, and fragment shading. Let's break down each of these stages to understand how they work together to create the final image. Vertex shading is the first step in the pipeline. During this stage, the graphics processor takes all the 3D vertices that make up the game world and transforms them into 2D screen coordinates. This involves multiple mathematical transformations using matrices. First, objects are transformed from their local coordinate space into world space, then from world space into camera space, and finally projected onto the 2D screen. Think of it like taking a photograph. The objects in the real world exist in 3 dimensions, but when you take a picture, you're capturing a 2D representation of that 3D scene. The same principle applies in video games, except instead of using a physical camera, we're using virtual cameras and mathematical transformations. The complexity of modern games is staggering. A single frame might contain millions of vertices. For example, a detailed character model might have 100,000 vertices, and a typical scene could have dozens of characters, plus buildings, vehicles, vegetation, and other objects. Modern graphics cards are specifically designed to handle these massive calculations efficiently, with thousands of processing cores working in parallel. Once the vertices have been transformed into screen space, the next step is rasterization. This is where the graphics processor determines which pixels on your screen need to be filled in to represent the triangles formed by these vertices. It's similar to connecting the dots in a drawing, but instead of drawing lines, the processor is filling in entire shapes. Rasterization also handles the visibility problem, determining which objects are visible and which are hidden behind other objects. This is accomplished using a depth buffer, also known as a Z-buffer, which keeps track of the distance of each pixel from the camera. When multiple objects overlap, only the closest object at each pixel is displayed. The final major stage is fragment shading, where the actual colors of the pixels are determined. This is where much of the visual magic happens. Fragment shaders calculate how light interacts with surfaces, apply textures, and create effects like reflections, shadows, and transparency. Modern games use incredibly sophisticated shading techniques. Physical-based rendering, PBR, simulates how different materials interact with light in the real world. For example, metal surfaces will have sharp, bright reflections, while rough surfaces like concrete will diffuse light more evenly. These calculations happen for every pixel, every frame, often more than 60 times per second. Textures play a crucial role in adding detail to 3D models. Instead of modeling every tiny surface detail geometrically, which would require an impractical number of triangles, games use image files called textures that are wrapped around the 3D models. These aren't just color maps. Modern games use multiple texture types for different properties. Normal maps simulate surface detail by telling the shader how light should bounce off each pixel. Roughness maps control how shiny or matte a surface appears. Ambient occlusion maps add subtle shadows in crevices and corners. But creating realistic graphics isn't just about raw mathematical precision. Game developers employ numerous tricks and optimizations to create convincing visuals while maintaining good performance. Level of detail (LOD) systems use simpler models for distant objects where fine detail wouldn't be visible anyway. Culling systems prevent the rendering of objects that aren't currently visible to the player. These optimizations are crucial because games need to maintain smooth performance while rendering complex scenes in real time. The evolution of graphics technology continues to accelerate. Ray tracing, long considered the holy grail of computer graphics, is now possible in real time thanks to specialized hardware in modern graphics cards. This technique simulates the actual behavior of light rays, creating more accurate reflections, shadows, and global illumination effects than traditional rendering methods. Machine learning is also revolutionizing game graphics. Technologies like DLSS, deep learning supersampling, use AI to generate high-resolution images from lower-resolution renders, improving performance while maintaining visual quality. This is particularly important for demanding features like ray tracing or high refresh rate displays. The memory requirements for modern game graphics are enormous. High-resolution textures, complex models, and sophisticated effects can easily consume gigabytes of video memory. This is why modern graphics cards come with large amounts of fast VRAM, and why game installations have grown so large. Looking to the future, we're seeing the emergence of new technologies that could further revolutionize game graphics. Real-time path tracing, which is an even more accurate form of ray tracing, is becoming more feasible. Procedural generation techniques are becoming more sophisticated, allowing games to create vast, detailed worlds without manually modeling every object. Neural rendering techniques are beginning to blur the line between traditional computer graphics and AI-generated imagery. The field of video game graphics is a perfect example of how art and technology intersect. It combines the creative vision of artists with the technical precision of computer science and the processing power of modern hardware. Every frame you see in a modern game represents countless calculations and optimizations, all happening in milliseconds to create the illusion of a living, breathing world. Understanding how video game graphics work isn't just academic knowledge, it's increasingly relevant to many fields beyond gaming. The same techniques are used in architectural visualization, medical imaging, scientific simulation, and virtual reality applications. As our world becomes more digital, the ability to create and understand 3D graphics becomes more valuable. Whether you're a gamer, a developer, or simply someone interested in technology, appreciating the complexity and ingenuity behind video game graphics can enhance your understanding of how modern digital experiences are created. The next time you play a game, take a moment to consider the incredible technology working behind the scenes to create the world you're exploring.